Next up, we have a talk on extreme scale earthquake simulation with MVAPICH. So we have two speakers for this talk. So Dr. Yifeng Ku, he heads the high performance geocomputing lab at SDSC. And he also helped to establish the Southern California Earthquake Center as a world leader in advancing HPC in earthquake system science. So he's the first speaker, and his colleague, Dr. T. Yang Ye, who's a postdoctoral researcher at SDSU's, apologies, works in collaboration with SDSC on the development of advanced wave propagation simulation codes. So, please.
Thank you. So I'm going to talk about the earthquake simulation using MVAPICH. And this year, our focus is more about the more advanced, ADAPT-PODC, the future with topography, and this continuous mesh. For that, we invited Dr. Ye from San Diego State University to be part of it. And he is a seismologist. He is going to provide some numerical method background and also, show us about some recent results using the ADAPT code with topography. So first, acknowledgement. This is a larger scale collaboration, and the first of all is a SCAC. Now it's called the Statewide California Earthquake Center, located at USC, and it's majority the funding comes from NSF through different programs. We also have TAC support both allocation, and it's called ARAC allocation, and also the CSA support through NSF SCCF program. And also we work with DK's group here and at Ohio State University, and as part of the CSSI program project. So in addition, we also have a larger allocation and from inside, and particularly from Frontier running on the AMD machine. So when we talk about the seismic band, they are from 10,000 seconds in period to a fraction of seconds, and associated with engineering interest is between 0.1 hertz to 10 hertz, and so move to higher frequencies, the computation is more expensive. With that in mind, we have developed the code, ADAPT-PODC code, for larger scale simulation. So this is with elastodynamics equation to solve the coupled system of PDE, second order in time, fourth order in space, and also with staggered grid split node in the formation of the boundary condition for dynamic rupture simulations. So Taeyang is going to be talk more about the numerical method later on. So to be accurate with the model, we have to improve the physics. Over the years, we changed quite some things from the fault roughness and to the plasticity, particularly lately for the frequency-dependent attenuation, and also the multi-surface non-linearity. Those are its important features with the ADAPT-PODC code, where it stands out and compared to other large-scale earthquake simulation codes. And so the image we show here is from the Supercomputing 2016 running linear and nonlinear simulation comparisons using the GPU code. And later on, last year we did a larger simulation at the full machine scale at the TAC using the Frontier machine. That's the first dynamic modeling, combine rupture, dynamic rupture simulation, and also the wave propagation simulation in a single step, and using the checkout scenario. So to do those way like topography implementation, it will require more computation. It's roughly 1.3 times, depends on the setup. So this is it's more expensive compared to linear solution. On the other side, if you look at the multi-surface non-linearity, this is much more expensive. So typically we think between the 20 to 30 times expensive compared to linear solution. So that's where more computational resources are needed. So first looking to the at PODC, the performance between the different versions on different systems over the years. We have a comparison about the performance, how it achieved on different machines. So latest about the Frontier and also the Frontier and the Frontier first machines. And we also had some comparison of the performance on TAG Lone Star. It's as experiment, and to compare using default Intel MPI and also the MVAPICH, and the MVAPICH with GDR and with also on-the-fly compression, how this performance is going to make some difference. So here is the some results using the linear code. We see roughly you can up to the 16 nodes you can get up to 154% performance gain. And so if you look into the we created a matrix called M loops. It's millions of lattice update per second, and that's to measure about the performance of the code, the efficiency. If you look into in the past, if you look at the K20X, it's a Titan machine at Oak Ridge, and compared to what we have today, like expense, it's A100 using NVLink, and also the Lone Star A100 and with the InfiniBand. So you see how this speed up, it's over the years has become roughly on expense we get 3.5 times speed up. So on the Lone Star, without tuning using the default Intel MPI, we get 1.6 times speed up, but with the MVAPICH and also the on-the-fly compression, we are getting 3.8 times speed up. So in the latest system, like the Vista attack, Grasshopper 200, we were getting 15 times speed up. So what I'm trying to show here is, yeah, the interconnect is important, but the compiler is also very important. So even you have a slower interconnect, if you have the right the compiler and the GPU aware the features and also the compression, so you can get even better performance. So now we talk about the topo code, and this is recently ported to the system using the HIP, and we show actually the code on the Frontier up to I think we were running for up to 4,000 nodes, and we see actually excellent weak scaling. It's I think it's extremely good. It's more than 100% of the weak scaling parallel efficiency. So if we look compare a little more, and we also implemented the GPU aware the feature into this code, which is still need to be modified, and compare to the linear code. and the top code. So in terms of the parallel efficiency, and you see the parallel efficiency with top code is even better, and particularly with the GDR feature there at the 4,000 nodes level, you see the performance is even better. Roughly, we get like 13 to 14% additional performance gain using the GPU-aware the feature. So computation requirement in the PODC, this code has been used in many different cases. And we have both CPU and GPU code. With the CPU code, for example, the F3D is for tomography code. And so that's roughly at current we run upon the 2 hosts. For the Southern California domain. And DynaShack is something I've called, it's a dynamic rupture modeling we did last year at the Tech, the Frontier machine. And that's the current, basically the status. We see computation requirement is mesh size, NX, NY, Z, multiplied by the time steps. So that kind of, over the last decade, we have increased this requirement by 4 orders of magnitude. So for next 2 years roughly, and so looking to the inside allocation and also the tech, the ARAC allocation, we want to move a little bit more, 1 order magnitude and further. The shack out and the sub-shack both code using the GPU code. And the sub-shack is using the linear GPU code. The shack out is now using the top code. That's what Dr. Ye is going to introduce more. And 5 years from now, and we are going to require 4 more order of magnitude. So that's what basically the challenge, the computational challenge and requirement in terms of this project. So I stop here so you can continue.
Hi everyone. My name is Tae Young. I'm a computational seismologist. It's my first time here at CS conference. So it's a fun fact. So seismology is actually a branch of physics that studies seismic waves. So I'm sorry that I can't predict when and where the next big one will happen. That is none of my concern, and that's not my goal. My job as a computational seismologist is to predict ground motions generated by, let's say, earthquakes or explosions. That's my job. And we want to do that very accurately. That's our goal. So if we go with, there are actually many different ways to do that. If we want to go with 3D numerical simulations like AWP, ODC, it's very computationally intensive. And oftentimes we need to use thousands of GPUs for a couple of hours just to run single calculation. And that's why we remain close relationship with our friends in this computer science. So today I would like to talk about how we have been taking advantage of achievements in this computer science to support our growing ambitions. So the wave propagation simulation code AWP ODC is a 4th order accurate stagger grid finite difference code. And when I say stagger grid, some people might not be familiar with what I mean. If you please look at the diagram here, when I say stagger grid, it means when we're solving for velocity and stress equation, that's a wave equation, the location of the velocities and stress are not at the same place. So they're not co-located. And they're actually offset by half a grid point. And that's why we said it's a stagger grid finite difference. There are pros and cons about this methods, but I think there's more goods than bads. So that's why we still love it. So it's at well, it has been through a lot of recent updates, and then we're going to talk about that today. It's GPU enabled and it's highly scalable, thanks to our friends in the computer science, Yifeng's group. And we have a curvilinear grids and discontinuous mesh features that I will be talking about in a minute. And we've developed these new features on Summit at Oak Ridge supercomputers with NVIDIA GPUs, and we verified and deployed HIP version, and we're actually performing full production runs on Frontier, also at Oak Ridge with AMD GPUs. So, and at last, I think I'm going to show how we use, how this teamwork makes all the magic happen in our most recent ground motion simulations. So let's get to the first new feature in this AWP code. We're going to talk about the curvilinear grid feature. So previously we used what we call the Cartesian grids, that is right here. And because of the nature of the Cartesian grids, we have to assume that the surface of the Earth is flat. It's completely flat. But we know it's not true. It's anything but flat. We have mountains, we have valleys, we have different features at the surface of the Earth. So we now implement a curvilinear grids to include the actual surface topography. So as you can see, that's right here on the right. And what we do is we specify a mapping function so that everything here on the Cartesian grid is going to be mapped to a new location, and we're actually matching the actual topographic elevation everywhere. But the horizontal locations of the grids are remaining the same. We are only stretching the grids vertically. So the problem is when we work with the Cartesian grids, all the basis vectors like the x, y, and z, they're naturally orthogonal. So there's no problem with that. It's very natural. We can approximate all the physical quantities numerically very naturally. But we were talking about curvilinear grids. The basis vectors are no longer, x, y, and z. It's going to be defined locally. So the orthogonality is defined locally, and that complicates the governing equation we're trying to solve numerically. So let's look at here. We have to define a local basis vector. We have the covariance basis vector that's tangential to the curvilinear grid line, and we also have a contravariant basis vector that's orthogonal to the covariant basis vector, and we are establishing orthogonality here. So we define these basis vectors locally, and like I said, that will allow us to transform the Cartesian coordinate form to the curvilinear form. We now have a new governing equation to solve if we have a curvilinear grid. So you can see there are extra terms right here. There's a J, and there is an basis vector right here to take care of. And let's see how we are gonna deal with this. So I'm not going to go too much into detail, but I'm going to just show you the challenge that we're facing. So if we look at if we expand all these terms, we can see there are extra terms right here. And then the first thing that you can see is that if this is a very generalized equation, so the Cartesian form is actually the special case of this generalized form. This can be recovered to the Cartesian form if this condition is true. And then we can take a look at this AKK, the diagonal terms. They're easy to implement in the numerical scheme because they also exist in the Cartesian grids, and then we can just follow the same business to approximate the velocity and stress in the numerical methods. But the off-diagonal terms they're not so easy, and then we have to implement some interpolation and differencing operator in order to approximate the velocity and stress in the curvilinear grids. But anyhow, this is this is done carefully, and then the implementation has been has been there. So I think the final thing to check is that's additional work, that's adding the computational overhead to the code. We're curious about whether that's going to change the scalability of the code, because that's the key to our success using this code. So we performed the rescaling tests on the NVIDIA V100 machine. It's on Summit at Oak Ridge, and up to thousands of GPUs, and we're still seeing very similar time needed for each time step. So that means we are having a very good scalability, even with the new topography curvilinear grid feature. And then, of course, we need to verify the results with the a different numerical method, just to make sure that our calculation is still accurate. And so this is the result that we're comparing the results with the SpecFAM. That's the spectral element code. And then we are in great agreements with the SpecFAM's results. So now we're confident that this code is ready to use, and curvilinear method, it's stable and it's accurate. And let's talk about the second new feature. This is motivated by the performance, improving the performance. So I think on top of that, we're going to talk about how we can have the grid coarsening strategy. And the reason is that in our Earth structure, the seismic wave speed tends to increase with depth. And the higher seismic wave speed corresponds to longer wavelengths. So if we still use the same grid spacing all the way through from top to bottom of our model, the same small grid spacing is going to give us absolutely no benefits. So it's only going to occupy excessive amount of GPU memory. So we decided to implement a factor of 3 grid coarsening strategy. And we're not only downsampling the wave field, we're also downsampling the description on the ground seismic structures. And in order to do this, we need an overlap zone like here to do the data exchange. And what we want is a seamless wave propagation through the overlap zone without creating any artifacts. So there are a couple things that we need to do in order to achieve this. Because we're coarsening the grid spacing, there needs to be a downsampling process there. And because the coarser mesh has a co-located points inside the overlap zone, so can we just copy and paste the velocity and stress value from the finer mesh to the coarser mesh? And unfortunately, that's not going to work. It's proven unstable. So how do we do this? So in Niet et al. 2017, this paper, it's documented that we actually need to filter the wave field to get rid of the information of shorter wavelengths, so that they are not hovering around and causing instabilities. And then the filter wave field got interpolated onto the coarser grids. And it's been shown that this is going to be stable and accurate. So we verify the results. It's been shown that as long as in the overlap zone, we're still maintaining the resolution of at least 7 point per minimum wavelengths, we're going to get a 0.995 at least correlation coefficient when we're comparing with the uniform grid spacing. So I'm showing you how this works to the right here. So this is a actually the velocity, the S-wave velocity transects. So the model goes from the surface all the way down to 100-kilometer depths. And if we have the discontinuous mesh feature, we can actually have an overlap zone at around 25-kilometer depths. And the grid spacing below 25-kilometer depths gets 3 times bigger from 100 meter to 300 meter. So when we're using this feature, we're going to cut down the the model size below 25-kilometer depth by a factor of 27, and that becomes negligible. And the entire cost of computation is expected to be reduced by 75%. So we're not going to use that much of the GPU memory. We're not going to use too much of the time to do the computation for the entire domain. So now we're going to talk about how we use these new features in our most recent ground motion simulations. So I'm from Southern California. When it comes to ground motion simulations, there's no better example than the shakeout scenario. This is still a big thing for school age kids. They still have a shakeout drill because they want to promote the awareness and preparedness of the impacts from the major seismic events in Southern California. And to talk about this, we need to go back. We need to go back in time. In 2008, the United States Geological Survey initiated a shakeout scenario in order to promote their awareness, and preparedness for the impacts of the major events. And the process of an earthquake is not, it doesn't occur at a single point in space. It's actually a distributed process along the way, the entire fault plane. So it's a multi-institutional project, and a lot of scientists use the best available science to determine where the fault plane is and how to describe the fault slip as a function of space and time. And that was the best available science at the time. And they were focusing on the southern portion of the San Andreas faults, as you can see right here. So that was the snapshot video from the 2008 simulation. And then we are going to use this scenario as the representation of the big one. So this is our base seismic source model. And the description of the fault, source rupture model is only the first part of this study, because it's really hard for the general public to know what to expect if they're just presented with a source rupture model, right? So in order to make this a little bit more useful, we need to predict how large the ground motions are, how large the ground motion can be expected throughout the Southern California. So that's when the numerical simulation codes like AWP, ODC come into play. So back in 2008, numerical simulation predicted unexpectedly strong basin amplification, which is known as the waveguide effects. It's an energy channeling along the interconnected basin into the Los Angeles basin. So that's what I'm highlighting here, right here. And you can clearly see that on here and also on the snapshots over here. So that's what we call the waveguide effects. And if you look at the value, it can be as large as 1.78 G. That's acceleration. And that's acceleration at 3 seconds. So if you look at that, the 3-second spectral acceleration, that corresponds to, I would say, around 30-story building response. So you can imagine why this actually freaked a lot of people out at the time. And but we started to think, was the best available science back in 2008, it was 16 years ago, still the best available science right now? So we're going to find out. So in fact, it's not just a simulation code being updated over the past 16 years. There is a lot of improvements going on, especially our knowledge on the underground structure. So in Southern California, even back in 2008, we have to say that we have very good understanding on the underground structure inside the major basins. But later on, seismologists started to use more advanced method to image the underground structures. And this is greatly improving the spatial resolution of 3D velocity structures. So as you can see, if we're going outside of the basin and comparing with the one on top, that's a huge difference. So we know the underground structure a lot better than before. And then there's also a lot of local updates from this panel down to this panel. those in the outlines, those are the newer velocity structure. And then the reason why we're using these is because they're along the way, the path of the seismic energy propagating into the basin. So we use them. And then what we do is, because we have a really good scalable code, and then that allows us to run many cases to show the contribution of each changes in our understanding on the ground velocity structure. So we actually go from the starting model, that's the panel A, all the way to panel H. So that's our starting model. That's our final model. So you can clearly see the huge difference. It's mostly the reduction on the predicted ground motion. So then there we realize how important this is to revisit all these studies using the better code, more realistic model, just to make sure that we're really up to date on the prediction on the ground motion for this scenario like this. So this is what we're saying. We're going to see the huge reduction on the predicted ground motion in the basin. It's up to 50 and 70% reduction. And then are you going to ask, hey, if you do this 10 years later, are you going to say it's different again? And I would say it's possible, but it's unlikely, because this time we validate this model carefully. We simulated this small earthquake, and then we're making sure that this model is going to give us a very good recovery to what we're observing in the basin. So this time, I think we're doing a lot better than 2008, using the much better tool and the much better model. So if we compare the snapshots, this is the Los Angeles, that's the old model, and that's the new model. You can see in the old model, we have a lot of strong amplification there, but in the new model, this is the city of Los Angeles. It's not going to see such a strong amplification in our final model. So I think this is probably the good news for people living in Southern California, but this is only representing the shakeout scenario. So I think this is the starting point of our study. I think we're going to keep continuing collaboration with the San Diego Supercomputing Center to have more ambitious work in making some even more societal impacts. So that's all about my presentation. Thank you.